Well, our goal is to find a matrix that transforms V1 to 1/2 V1 and V2 to 2V2, right? Well, we don't know the components of V1 and we don't know the components of V2, okay? But since I drew them on the unit circle and they look something like this, still lopsided, okay? Well, I think I had V1 out about here. I think I had V2 about here, right? Okay? Well, let's just estimate. I mean, this is a unit circle, so the components of V1 look like about, I mean, here's the I vector, and here's the J vector, right? Well, it looks like V1 is then going to be about, what, 1.6 I plus 0.7 J. Okay? So let's just use that. Whether that's accurate or not, it illustrates the process. So this is, what did I say, 1.6? I think it's 1.6 I plus 0.7 J. And V2 is what? Well, you know, it's this way and this way. It looks like it goes about negative 0.2 I plus, it looks like about 0.7 J, about the same as the other one in the J direction. Do we understand how I made those estimates? Okay, you need to have a visual. Because if all you do is start manipulating matrices and simultaneous equations, which is what everything reduces to, okay? But you do it with matrices because it's easier and more compact and your calculator will do it, okay? Not that I'm going to let you do much of that. Okay. We can do this, right? Okay, so we can estimate these. Just from the picture, we can make a reasonable estimate, and we can make reasonable estimates of what the transformations would look like, right? And we're not going to be overly accurate, but at least we have a picture of what's going on, so now we can hang on to that. We can hang the matrices and the simultaneous equations and calculations onto the picture. It is a very important picture. Okay, as you'll see. Okay, so now we want a matrix, okay, that if we multiply by 1.6.7 gives us, well, this is supposed to shrink down to half, right? Okay? Make sense? Okay? And we also want that matrix it's got to be the same matrix because you only have one matrix to define the transformation. This matrix multiplied by negative 0.2.7 should equal 2. Times 1.6.7, right? Okay?
Negative 0.2.7.
Because shouldn't it be 2 times?
Yeah, it should be
V2?
negative 2.7, negative 0.2. Okay? Now theoretically, does this give us enough information to determine the numbers in this matrix? Okay, well, let's just say the numbers in the matrix are A, B, C, and D. We won't usually use A, B, C, and D, but for 2 by 2 matrices, we will sometimes. We'll usually label these by row and column. So this is the first row, first column. So we maybe call this A11 First row, second column be A12. Second row, first column be A21, and then A22. But we'll do that when time comes, okay? And if we go to, anything bigger than a 2x2 matrix, we end up with too darn many letters, and we will use the subscripts, okay? But for now, we can get by with this. Well, how many unknowns do we have? 4 unknowns. How many equations can we get in those 4 unknowns? Well, I'll give you a hint. AB times 1.6.7 is 1.6A plus 0.7B. And that should equal 1/2 of 1.6, right? So we can get the equation 1.6A plus 0.7B equals 1/2 of 1.6, right? And then we get 1.6C plus 0.7D equals 1/2 of 0.7. Can we solve these equations for A, B, C, and D? Well, we've only got 2 equations and we've got 4 unknowns, right? So we can't do it. Of course, we got this equation here, which gives us 2 more equations. Now we got 4 equations and 4 unknowns, and we can solve the things, although we're not going to. We're going to use inverse matrices, okay? So now I can write it out. We got negative 0.2A plus 0.7B equals 2 times negative 0.2, and negative 0.2AC plus 0.7D equals 2 times 0.7. Okay? Now we have 4 equations. It can be solved, assuming there's not any redundancy, and there isn't because these vectors aren't parallel, so it is going to work out. Okay? If the vectors are parallel, then you might have the same coefficients here to give you one number, and the same coefficients here to give you a different number, and they'll be inconsistent. It's like you're saying 2A plus 3B equals 12, but 2A plus 3B equals negative 3. Can't be. Okay? If 2 of these vectors were parallel, though, you might end up with that. You would end up with something like that. Okay. So, we see that we can find this matrix. And this really isn't that much trouble. It's a little bit of a pain. It'd be messy. You want to avoid it. You want to try to avoid it. You can't avoid it all. Okay, so let's see what we could do in terms of matrix equations.